Hi there! So far we considered vectors in a two-dimensional space. We have seen applications like analyzing forces and the flow of water. But we live in a three-dimensional world, so it makes sense to also consider vectors in 3 dimensions. That is what we're going to do in this video. And you will see that calculations with vectors in 3 dimensions are basically the same as in 2 dimensions. In 2 dimensions we have an x and a y direction. In 3 dimensions there's also a z direction, so we can represent points in 3-dimensional space with 3 coordinates. In the picture you see the point 2, 4, 3 in orange. The vector from the origin to this point is the vector 2, 4, 3, which is the vector which moves 2 in the x direction, 4 in the y direction and 3 in the z direction. Just as in 2 dimensions, vectors have no fixed starting point, so we can move this vector around without changing it. Let's try to calculate the norm of our vector. Remember that this is just the length of the arrow. As you can see in the picture, the vector v is the hypotenuse in the right triangle OBC. So we can use the Pythagorean theorem to calculate its length. Then the norm of v squared is equal to the norm of the vector bc squared plus the norm of oc squared. So you can see that the length of bc is 3, so now we need to calculate the length of oc. We can do this using the triangle OCD in the xy plane. We see that the length of OC squared is equal to 2 squared plus 4 squared. So the length of the vector 2, 4, 3 squared is 2 squared plus 4 squared plus 3 squared, that is 29. Such a calculation can of course be done with any 3-dimensional vector. In general, the length of the vector ABC is the square root of a squared plus b squared plus c squared. You see, apart from the term c squared, this looks very much like the formula for the length of a 2-dimensional vector. So, what about scalar multiplication? Well, multiplying by a positive scalar k still means that we get a vector with the same direction which has k times the length of the original vector. And if k is a negative scalar, the direction is reversed. The calculation is the same as in 2 dimensions. We have to multiply each component of the vector by k. Addition of 2 vectors is still putting them head to toe, and the calculation is the same as for 2-dimensional vectors. You can add them component-wise. For example, take the vector 2, 4, 3 again and add the vector 1, 1, 3. Then the resulting vector is 3, 5, 6. What may be a bit surprising is that the angle formula that you have seen for 2-dimensional vectors also works in 3 dimensions. In this case, the dot product of 2 vectors v and w is v1w1 plus v2w2 plus v3w3. Let's try to use this formula to find angles between vectors in 3-dimensional space. As an example, consider a methane molecule. This consists of 4 hydrogen atoms located at the corners of a tetrahedron, and they are attached to 1 carbon atom in the center. We use the angle formula to calculate the bond angle, which is the angle alpha between the vectors v and w in the picture. We can choose coordinates such that the carbon atom is at the origin and the other atoms have coordinates plus and minus 1. Then v is the vector 1, minus 1, minus 1, and w is minus 1, 1, minus 1. From the angle formula, we find that the cosine of alpha equals minus 1/3, so that alpha is approximately 109 degrees. You see that calculations with 3-dimensional vectors are basically the same as with 2-dimensional vectors. You can practice with such calculations in the exercises. Good luck!